Good morning, all. We Applied Electronics and Instrumentation Department of Mount Sion College of Engineering proudly presents a webinar on backstepping controller design for industrial process, which is going to be presented by Dr. Anish V. He's an assistant professor in electronics and communication in Christ deemed to be University in Bangalore. On behalf of Mount Sion College and Department of Applied Electronics and Instrumentation, I would like to extend a warm welcome to all of you. It is my immense pleasure to welcome our chief guest, Dr. Anish P. On behalf of Applied Electronics and Instrumentation Department, I welcome you, sir. I would like to welcome our principal, Dr. Matthew K., Vice Principal Professor Thomas George, all department HODs, and all faculty members to this event. Once again, a warm welcome for all the participants for this wonderful webinar. I hope it will be a valuable and informative session. Now I invite Dr. Anish V to handle this session. Thank you.
Yeah, thank you, Adria ma'am. Am I audible and clear?
Yes, sir.
Hello, ma'am. Am I audible and clear? Hello? Yeah, thank you, Richard. Ciao.
Go ahead.
It's funny. Yeah, first of all, thank you so much, Mount Sion College Applied Electronics and Instrumentation Department, for giving me an opportunity like this. So I'm just in front of very few familiar names from the old my Mount Sion days. So thank you so much, Thomas George, sir, the head of the Department of AE, and I to make this moment. So I'm not wasting the time. I'm just directly going to my presentation. My scene is okay to all? Hello?
Yes, sir. Is it visible?
Yeah, thank you. I am extremely sorry. I'm not good with Google Meet. Okay. The topic we are going to discuss here is backstepping technique or backstepping controller design for industry processes. Okay. If in between any interruption in the network, you people can able to unmute and tell me. That is very useful and very good for the easiness communications.
Sure.
Ma'am, is there a requirement of switching on the camera? Adira, ma'am?
Sir. Hello,
Adira,
sir.
Yeah. Is
Hello.
it any requirement?
Hello, sir. Can you hear me?
Yes, I can hear you, ma'am. And then my question is that is there any requirement of switching on the camera?
Yes, sir.
Yeah, okay. Thank you. I think, okay, now we can go to the presentation, the backstepping controller design for industry processes. So I'm Dr. Anish V. I'm working as an assistant professor in the Department of Electronics and Communication Engineering of Christ University, Bangalore. So here I'm just talking almost 45 minutes purely based on a new concept. It's not a new concept. It is called backstepping technique. The technique is more or less similar to the design of a controller. We are using the normal conventional PPI, PID, or maybe in the advanced versions of neurofuzzy controllers. All these things we are clubbing and to a new era called backstepping controller. It is absolutely different than what you are thinking about the PPI and all these concepts. So before going to that, I know that few people as a webinar may know about the controller design, few people may not. So that I'm just quickly going through a certain area like what is a controller, what is a control system, what will be the control actions, what are the different type of controllers. And all these things I'm just going through that particular point. So if you're talking about a controller, we know that if it has a process, we need to control the particular process. So the particular process is controlled by a particular controlled systems. We can call it as a controller, control system. That means if we are having a process, we need to keep certain controllers in front of the process to make that system at our desired level. So the control system can classify into two based on the structure, open loop or closed loop. We know that open loop is easy to manufacture and easy to implement, reliable and all. But the closed loop system is not that much. It is little more complex in structure. All these things are known to all who belongs to the lower semesters of your bachelor's of engineering. So now we have more important thing before doing that. What is a control architecture? Maybe you people are not discussed much more with what is a control architecture. So the control architecture, if I have a raw material and I'm just going to make a transformation of that particular process to a part or a product. That part or product, after that I have a scrap or waste. So converting the raw material to a part or a product, I require certain transformation process. The transformation process of that particular raw material to a part or a product have 4 levels structure or 4 level architecture. It's called level 0, level 1, level 2, level 3, and level 4. That is, from the raw material, we need to sense what is the sensor, which material is that, or which type of actuator system we need to use for that. All these things belongs to the level 0 of our process. Then, coming to the sensors and all these things, we are connecting to a automatic control or machine controller. The machine controller stands in the level 1 of architecture. In automatic control strategy, we know that a lot of controllers we can use, from the conventional controllers to advanced controllers like neurofuzzy and all these things. Then, little more advanced level is level 2. We need to do supervisory control. It is also known as cell control. What is supervisory control? You know that distributed control system. You know that what is SCADA. All these things belongs to supervisory control or cell control. The next level is level 3. It's a plant control. That is the production of the particular plant, quality of the plant, safety measurement of the plant, all these things under the level 3. Then the enterprise control. These are the 4 levels of control architecture. Level 0 to level 4. That means the implementation of the base sensor to the enterprise control, everything will be concluded in 4 different levels called the control architecture. In that, the device control to cell control belongs to industrial automation or shop floor control, and the plant control and enterprise control belongs to the business information or the business office control action. So these are the basic control architecture. Now, if we come into the term automatic control, we are having a certain plant or parameter. That parameter we are giving to a controller. The controller produces an output as an error signal. That error signal gives the particular actuator. Based on the actuator action, the particular process will be taking place. The process output be sensed with a sensor and we are connecting to the controller. So we know that input to the controller is the difference of the input parameter and the feedback signal from that. So the input controller is an error signal. Then you are much familiar with what are the different type of controllers. In the process dynamics and control, or in control system or control engineering, you people studied that what is proportional, integral, derivative, what is proportional, integral, proportional, derivative, and PID controllers. So any conventional controllers we can use for that. along with the latest or new controllers that is known as non-linear controllers. You know that PPI, PID and all these composite controllers can be applied in the linear system. In some cases, then we need to use the feedback linearization technique also for that particular process. Now, before going to that, we need to know what is process versus discrete industries. That means we are having two types of industries, process industry and discrete manufacturing industry. That means the terms may be like what is process, what is discrete manufacturing. That means one is fully based on amounts of materials and the next one is based on the quantities of material. Based on these two things, we can segregate the industry as process versus discrete. That is, the production operations are performed on amounts of material means we need to call it as process industry. And if we are going to production operations are performed on quantities of material, we need to know as discrete manufacturing industries. Based on this, then, before going to deal with what is backstepping, the important parameter need to know for all the people here are what is variable, what is a parameter, what are the continuous variable and parameters, discrete variables and parameters. In this particular graph, you people can see that a continuous analog variable starting in the point of almost 3.6 to the time at infinity in the continuous manner. That particular thing is known as continuous analog variable. That means from 0 to t the signal is continuously varying. At the same time, you can see that discrete variable other than binary, discrete binary variable signal or pulse signal. These are the different parameters we are normally dealing in our control signal. Maybe the signal will be a continuous signal, maybe the continuous signal will be a discrete variable other than binary signal. We know that binary signal means it can be a value of 0 or 1. But if it is a discrete variable other than binary. Now, if you look into the diagram, in that you can see that a variable moving from 0 to 3 as like a small strip of time. Right, we can make it as an impulse, or we can make it as a box function. Box function having an amplitude of 3. And we know that the third parameter variable is known as the pulse data. The pulse data means it will generate continuously or frequently after a particular interval of time. This is known as pulse data. Then the output of a process and input of a process, because if we are using a control structure, we need to take a process. For that particular process, we need to give certain input and we need to take certain outputs. So the input to the process is known as parameters and the output of the process is known as variables. So further in the discussion, we will talk the variable is not input of the process. We will take it as parameters and variables. Then, now the important thing, we already know that what is the types of controllers. Continuous controllers are there. Variables or parameters are continuous and analog. Discrete controllers are there. Variables or parameters are discrete, mostly binary in structure. So to maintain the value of an output at a desired level, that means our requirement. If we are having a system, we are having a set point, we are setting the set point and we are designing the particular control parameter. So in that particular point, the control parameter or the variable that we are to keep the particular level or the desired level. In that, how we can discriminate or how we can differentiate a controller other than our P, PI, PID controller. For industrial application, along with this controller, we are having fixed control structures. That is, continuous process controllers are regulatory control, feed-forward control, steady-state optimization, adaptive control. These are the 4 common control strategies we are using in our industrial processes, along with online search strategies, expert system, and neural network. These are the common terms. Now we are going to discuss with what is regulatory control, what is feed-forward control, what is steady-state optimization, and what is adaptive control. For this, these are the 4 different control structures we are normally using. Regulatory control, feed-forward control, optimal control, and adaptive control. So if we are talking about the regulatory control, this particular diagram, you can very easily identify that we are having certain input parameters. We are giving to the process produces certain output variables. So from the output variables, here we are taking some performance measure based on the input parameter. Whatever output we are obtaining for that particular thing, we are measuring or we are doing certain performance measures. So based on the performance measure, we are calling it as index of performance. And based on this index of performance and measured variable, that means using a sensor, the output variable we are measuring. Based on the measured variable and the index of performance we given to a controller, the controller required a target or a set point. So the performance target also we are taking that. Based on this particular controller adjusts the input parameter to obtain the desired level. This type of control action is known as regulatory control. It is more or less similar to a simple feedback structure. But here in simple feedback structure, we will check the output variable or the measured variable to the controller and we will compare with the set point and we will fix it. But here we are evaluating the performance measures and we are generating the index of performance to the particular system. And we are in this case also, the controllers we can give PID controller or PI controller or neurophacy controllers based on that. This is another control strategies. Then the next one is our feed forward controller. Simple. In the feed forward, that means we are, if you check to the regulatory control action in the process, you can see that there is no disturbance effect. We are not at all designing any disturbance. Here in the feedforward controller, we are mathematically model that particular disturbance. If any disturbance is acting on the system, we are checking the disturbance parameter. According to the disturbance parameter, we are mathematically modeling the disturbance and we are checking it with the controller. Similar to regulatory control, but the disturbance parameter also be considered in our feed-forward controller. Then we are coming to the optimal control or steady-state open-loop optimization or optimal control. These controllers are little more mathematically oriented controller. That means input parameter and output parameters both are there. Along with that, first, we measure the index of performance. Once the index of performance is measured, we need to mathematically model a process and the mathematical model of the process and index of performance. Both we will consider mathematically model. And along with that, for optimum input parameter values, we need to determine an algorithm. We are generating an algorithm for obtaining or for determining the optimum value. Based on these 3 parameters, the controller will function and adjust the parameter for the case of optimal control structure. That is, we are having the index of performance along with the mathematical model and an algorithm to determine the optimum input parameter. With these 3 parameters or 3 controls, terms, we are designing and we are implementing an adjustment in the input parameter. This is known as optimal control. Now, coming to the adaptive control structure. That means from the performance index or index of performance, we need to identify a system. After the identification, we need to make certain decisions on that. After that, the decision, we will do certain modifications. So identification, decision, modification, all these things will be taken care by a adaptive controller. Even if the process we are applying, we are having a fixed algorithm for this adaptive control. But the advantage of this controller is that if we are fixing this controller, I am just making that particular thing to a more disturbed area or less disturbed area. Wherever we place that particular controller, the controller will perform according to the disturbance or according to the condition. There will not be any disturbance or just happen based on the disturbance. Whatever area or whatever environment we are placing it, based on that, the particular system adapt and performs a better stabilized and better controlled structure. That is known as adaptive control strategy. Then, now, along with this, we are using the control named called backstepping controller. So, for the backstepping controller also, we need to add P or PID controllers. We can add. It is not at all exactly a controller. It is a control strategy or control algorithm. In that, certain requirements are there before doing to the backstepping controller. The main thing is that you should know about the Lyapunov stability criteria. What is system is asymptotically stable? What is recursive design process? What is this pure feedback form system or lower triangular form, skew matrices? So and you should be good in mathematics too for designing a backstepping controller. Now, we will talk about the topic. What is backstepping controller? So, from here, my presentation is going to make you familiarize that. What is a backstepping controller? What is the advantages of backstepping controller in comparison with our conventional controllers? How we can implement or how we can design a mathematical controller. For that, certain equation sets are there, because without that instruction sets or equation sets, I couldn't able to make this presentation complete. And if I'm orally talking all these things means it will not make you familiarize that what is this. At the end, it should be a guess. So that we are coming to the point, backstepping controller. So all of you studied about the stability. Stabilized system. One system is stable. A simple thing, if we are having a transfer function, having certain poles and zeros, we can tell that the particular system is stable based on the location of poles and zeros. Simple logic system is that if you are having a system, that particular system, in that particular system, all the poles are lying on the left side of the S-plane. We can tell that the system is stable. And if we tell that all the poles are lying on the right side of the S-plane, we can tell that the system is purely unstable. We can tell that if it is in the imaginary line, we can tell that that particular system is marginally stable, conditionally stable, or asymptotically stable. Based on this, we are having a Lyapunov-based controller structure. So a Lyapunov function means a radially unbounded function having positive semi-definite variable. Positive semi-definite variable means if we are having a function v of x, for x we are equal to 0, then v of 0 is equal to 0, and v of x should be greater than 0 for all grade. So this thing you already know in the control theories. So the Lyapunov-based controller design may be systematically tackled by a recursive design procedure called backstepping. That means we are having a system. To that particular system, we have to make it into different subsection. That means I am having a bulk process. That bulk process, I am just splitting into 3 subsystems. And to the 3 subsystems, I am going to implement a controller. After implementing the controller, I am just coming from the innermost system to the outermost system. From innermost to outermost system, at the level, I am stabilizing my innermost system. From that, after stabilizing it, I am just coming to the outer system. I am stabilizing that outer system, then I am coming to the outermost system, like that it is coming to the final system of stabilization. This type of stabilization technique is known as recursive design procedure. So this backstepping controller, if we want to apply this backstepping controller, the system should be pure on strict feedback form. Strict feedback form means it should be a lower triangular form system. What is lower triangular form system? The lower triangular form system means if you are considering a 3x3 matrix and we need to consider the diagonal elements, the below part or the bottom part of the diagonal elements should be 0. That each element should be in the top end of the particular matrix. So one example of backstepping controller equation is given here. Theta 1 is equal to f1 of theta 1 plus g1 of theta 1 theta 2. Theta 1 to theta n are our parameters or states. f1 and g1 are the known functions of the system. That means x dot is equal to ax plus bu concept. That means the state space model of the system. So if you modify this or if you implement this, psi1 dot is equal to f1 psi1 plus g1 psi1 psi2. Psi2 dot is equal to f2 psi1 psi2 plus g2 psi1 psi2 psi3. So if you are implementing it in a particular system, means you can see that the lower diagonal elements are 0. So it is a lower triangular form system. So if your system is not in the lower triangular form, your main objective of our backstepping controller is that we need to make that particular system into lower triangular form. Once if it is in the lower triangular form, then you can easily apply backstepping technique. Then, a typical feedback linearization approach in most cases lead to cancellation of useful nonlinearities. The backstepping design exhibits more flexibility compared to feedback linearization since it does not require the resulting input-output dynamics to be linear. Cancellation of potentially useful nonlinearities can be avoided, resulting in less complex controllers. That means if we are using a P, PI or PID controller, we cannot able to directly apply that controller to a nonlinear system. We need to do feedback linearization or any other linearization techniques. So that if it is a discrete case also, we need to linearize it. We need to take a system or controller based on that. Again, we need to convert back to that. Similarly, here for backstepping technique, we don't want that linearization technique. So based on that linearization technique, we cannot able to, or we can able to make the system. So we don't want any linearization technique. So whatever system we are having, if the response is purely non-linear, if the result is probably non-linear too, then we can apply this particular backstepping technique. Maybe you will get confused that how we can. That is, I told the system we need to make it into different subsystems. We are implementing controller to each subsystem. From the each subsystem, we will take back the system to the stabilized state, so that because of this subsystem formation, we can eliminate this non-linearities. Then, coming to the main idea is to use some of the state variables as virtual controls or pseudo controls, and depending upon the dynamic of each state, design intermediate control laws. That means we are designing a control law or virtual controls or control Lyapunov function based on this recursive procedure where the Lyapunov function is derived from the entire system. Then the recursive procedure can easily be expanded from the nominal case of a system augmented by an integrator. This is also referred as integrator backstepping. That is, if we are having a system, in here need to give certain control variables. Here what we need to do is that we are setting certain virtual controls. We are finding out the equation for controllers, and this virtual control equations we are giving to that particular subsystem. Based on this virtual control, we are stabilizing the system, and we are continuously stabilizing each subsystem coming to the outer system. This is the recursive structure. It is also known as integrator backstepping. So the term backstepping controller and the integrator backstepping is the same concept and same structure we are using. Then, now we are talking about the baseline design of a recursive design process of an integrator backstepping. That is, I'm just considering a simple system. I'm not making a complex system. A simple system having the term F and G I am using for the familiarization. That is, zeta, theta, so eta dot is equal to f of eta plus g of eta sigma. Sigma dot is equal to u. This is the thing. That is, Third point you can say that objective is to design a state feedback control law such that eta and sigma tends to 0 as t tends to infinity. At the time tends to infinity, my eta value and sigma value should be 0. You can see that f of n plus or f of eta plus g of eta z sigma. The system can be viewed as a cascade connection of two subsystems, f of eta, g of eta, zeta, sigma. So the first subsystem is with the sigma as input, and the second subsystem is an integrator. So the main design idea is to treat sigma as a virtual control input for the stabilization of eta. So eta dot is equal to f of eta plus g of eta sigma, and sigma dot is equal to u. One subsystem we are making into two cascade system. One system is with sigma as input and the second subsystem as an integrator. Now, how we can design this particular backstepping control law? So assume that there is a smooth state feedback control law. I am assuming a variable phi of eta with phi of 0 is equal to 0 such that the sigma value I am giving as a Lyapunov stabilized function having positive radially unbounded term. Then eta dot equal to f of eta plus g of eta phi of eta. The system is asymptotically stable. That is, if the particular system after giving a state feedback control law, it should be asymptotically stable. Once it is asymptotically stable, then only we can able to do the feedback linearization. In this condition also, we need to check the system is in lower triangular form or not. Then consider that for the choice of psi of eta, a Lyapunov function v of n, I need to do the partial differentiation of this Lyapunov function with respect to the term eta, and that particular term should be a positive definite. The positive definite means v of x is a function. If that particular term should be positive definite means if I am substituting eta is equal to 0 or whatever term it is, that particular term should be come to 0 condition. Then we need to take the error. The error signal is E0. E0 is the between the state sigma and phi of eta. This particular thing is known as pseudo control. The pseudo control term we need to find out. Then we will get a new equation for eta dot and error dot, E0 dot. Based on these two particular terms, we are designing this particular control law. So I know that as a newcomer, this design process is too much complicated. But once you are solving from your side means this is the easiest method to achieve the control action. Then since the term f, g, zeta, all these are non-variables for us. One advantage of the particular backstepping technique is it does not require a differentiator. That means in some cases, if our 10 comes to a constant term, the differentiator makes the system to 0. If the differentiator makes the system to 0 means we know that if you are using a derivative controller alone in the system, we cannot able to use that D alone. Why? Because if a constant error comes means that particular differentiator makes the system 0. If it makes the system 0 means the entire control structure comes to 0. That's the reason we call the D controller also one name called anticipatory control. That means it will anticipate it at 0 and it will not produce any result. Similarly, this is the main advantage of a backstepping technique. So we don't require a differentiator there. The entire thing is integration based. Then in this particular case, we are setting a input variable into the system is I plus phi dot. Then the first component has asymptotically stable origin when the input is 0. So every time you are deriving it, it should be asymptotically stable. If it is asymptotically stable, we need to set that particular system. Based on this, we are designing a control law. U is the control element or control input. So we are having a system in the name zeta is equal eta dot equal to f of eta plus g of eta psi, sigma dot equal to u. To that system, we are applying, making into two subsystems. We are applying control actions, checking the Lyapunov stability. We are substituting a control Lyapunov function, that is positive definite radially unbounded function, and we obtained our control input as a new term in this structure. This is almost fixed for all process designs. Now, maybe few of them people have a doubt that why we need to do this much mathematical calculation and why we cannot able to do a linearization technique and we can use a PID controller. Why backstepping is good? Now, you can see that this is a simulated response, what we are doing recently on research on backstepping technique. You can see that a blue fully oscillated wave and a red wave with less oscillations. What is the meaning of this? The blue one is a PID controller. The red one is a backstepping controller. This is a comparative analysis of a aerodynamic system having a flight, Boeing 737. That means the input 1, input 2, output 1, output 2, based on our pitch, roll, yaw, pitch, roll, and yaw formation. We designed this particular backstepping technique for the controller. It is a multiple input, multiple output system. So that you can see that if you look into this particular blue line, after 150 milliseconds or in between 150 to 200 milliseconds, the system is not achieving their stability. Still, it has certain oscillations. But with the help of this backstepping controller, the system will come to the settling point at the minimum level. Less than 50, I think it is less than 10 only, 10 milliseconds. That is the main advantage of backstepping. Here, the nonlinear structure, we didn't do any linearization technique, we didn't do any other mechanism. We simply divided the system based into aileron, pitch, yaw, roll. Like that, we made the subsystem and we implemented the controller. From that, we got a drastic. After that, first thing, as a researcher or as a research student or a master's program, if you design a controller and you got an output, yeah, my output is good, I'm not going to do anything further, and we cannot able to justify our answer. For that reason, we need to check the robustness analysis. What is the robustness analysis? Robustness analysis means to that system, we need to enter certain uncertainty. Based on the uncertainty, we need to check that how much stable the systems will come. That means here you can see that I am having the dotted line. This full wave represents an uncontrolled system. Then one light cyan line represents a controlled system. Then one red and violet line having minus 10% and 10%. What does it mean with this is I have a controlled, uncontrolled system having lot of oscillations. Then I have a controlled system having less oscillations. Then for the state variable, I added 10% uncertainty and minus 10% uncertainty. Based on this 10% and minus uncertainty, I check the stability of the system or the settling time of the system. Look at the graph. The left side one, it's a settling time, uncontrolled system and controlled system in milliseconds. Previously with the uncontrolled system, in that it's 338. If we are doing with a PID controller, 338 we can reduce it to 300. Or some cases of the finest tuning of Ziegler-Nichols or Cohen code, with the PID controller we can make it into 150. But it is a tedious task. Why? Because means the design process is too much complicated. But with this controlled system of a backstepping technique, we will get stability in 8.55 seconds. That means 338 to 8.55 milliseconds. In a quick second of time, our system gets stable. Thus, we check the robustness of the system with 10% and minus 10% uncertainty. If you are checking this robustness in a system, you know that you are having a matrix. X dot is equal to AX plus BU is the state variable. In that, how you can add a 10% and minus 10% uncertainty? That is, you can take the 10% of the state matrix A. Then for the next system, you can add A dash is equal to A plus 10% of A. The second case, A double dash is equal to A minus 10% of A. With that concern, if your system is achieving a settlement time in and around the actual system's settling time means you can tell that the particular system is in robust performance. So that you can have the controlled system. Okay, the first time we took as the from input 1 to input, uncontrolled one with the 338, the control system is 8.5, then I added uncertainty and I subtracted uncertainty of 10%. My settling time has a range of 8.28 to 10.1. So 8.28 to 10.1 means our system is stable. By that reason, I'm just requesting everyone to check a robustness check for entire system if you are doing modeling. Why? Because otherwise we cannot able to predict. If I'm adding a 10% uncertainty, some cases of my system may go to a unstabilized condition. If it is going to the unstabilized condition, we cannot claim that my controller is working fine. By that reason, robustness check should be completed for all the processes. Now, we can discuss that how this controller affect industry processes. Maybe as a instrumentation students, you studied interacting, non-interacting system. Maybe you studied interacting 2-tank, interacting 3-tank, interacting non-interacting 2-tank, non-interacting 3-tank and all. So I'm just making a simplest example here, how this backstepping technique can be based on that. Non-interacting 2-tank system. So I'm not explaining the theoretical concept because this topic is studying in the undergraduate level. So the system model is given, but one thing you need to remember that for this all modeling, we cannot able to take the steady state modeling. We require dynamic modeling of the system. That means the gravity, height, the width of the pipe, everything should be measured. So with this model, I have two equations, height of the tank if it is H1, height of tank 2 is H2. The system model have dH1 by dE, dH2 by dt. So in the two cases, what I am going to design using backstepping controller, that is, I am going to design a control input Vp of t for the system. Based on the control input, how my system will track the reference. At one point, backstepping technique is also known as reference tracking. That means whatever input we are giving to the system, according to the backstepping control action, the system response or output will follow that particular backstepping technique. Then, after modeling the system, I got a control input like this. Because it's a webinar, I cannot able to explain more on the mathematical modeling. The same process what we designed in the previous steps, we can further process. Then, if you come to the controller design strategy, this is our response. That means here the two conditions I made for your familiarization. I simulated a step-like input and I made a sinusoidal-like input. That means it's a sine wave. In this line here, the red line starting from 2 is my reference input. That means the set point of the system. From 0, one blue line is coming. It is our response of the system after applying a backstepping controller. That you can see that from 0, suddenly it is going along with this particular thing. But in the case of a PID controller or a controller, you should have certain oscillations in the beginning. After that only it will come to that particular state, or it will track the particular feedback. This particular point is the main and utmost advantages of this particular system. That means reference tracking. If the controller and Lyapunov functions are pakka, our system will follow the reference tracking at the earliest with no disturbances, no errors in the system. It's something like an adaptive system. This is the again for the checking. You can see that here the particular system is oscillating very slowly. But again, we changed the oscillations, continuous oscillations. So even if this much continuous oscillations are there to in less time period, then too you can see that every aspects, this dotted line is the reference signal and the continuous red line is our system output. Based on the backstepping technique, this particular system follows the same reference tracking. Then coming to a little more advanced, maybe you people heard about a continuous stirred tank reactor. It is known as CSTR. It's a mixing. We are giving certain input to the process. Okay, it's 10, 11. Okay, I have 15 more minutes. I will try to wind up in 5 to 10. So this particular process, it has an input here. Based on the mixing and reaction having place, we are having a coolant chamber here. Then we are taking the product out here. So my particular aim or my objective is to regulate the concentration of the product B. That means B dot is equal to A, the input. After that, A, B, C, D are there. B is my product. A and B are my product. A is the input. B is the product. C and D are my byproducts. So we need to make the concentration of the product B at a particular level. For that particular level concentration, I made this line for my reference tracking. It is like a step input. After 100 seconds, it will step up to 1.12 from 1.09. So in this case, you can see that once I increase my step size, initially a reference tracking signal has a jerk. The concentration comes down, but suddenly it will rise, and once it's stable in minimum time, in 100 seconds. Similarly, for every cases, our particular process or continuous to tilt-tank reactor with the backstepping controller will work fine. This is also another example for the simulation. So here we gave a step input to the system. You can see that the system tracking is very easy. But here you can see that it's a box function. Having an initial step up, then after that we are doing step down. Even with step up and step down, our responses is somewhat lying near that. But with the case of a PID controller, the system cannot able to make this much stabilized performance. It will take too much oscillations in between the peak of the spike and in the step down cases also. By that reason, this backstepping technique is the most adapted one for the industry control actions. Then this is the reactor output again, having a continuous wave structure. This particular dotted line is the reactor output and is the reference trajectory. Whatever actions we are giving here, in many cases, this backstepping controller will come back to that particular process. Then, the next industry process, how it affects with the binary distillation column. All these things with the PID controller is well defined by the scientist named Leuben, W.L. Leuben. Leuben is a chemist, it's a German chemist. He designed a book called Distillation Column, a textbook is still there. He already designed all controllers with a PID controller with a different control strategies. As an instrumentation engineer, maybe I don't know as per the KTU, but the old MG University, you studied these things in, I think, the process dynamics and control, 50 unit, in that there is a case study. But I don't know that particular thing is available in the current syllabus or not. So there is a case study, control strategies. So I just make you just a glimpse of what is this binary distillation column. It is a separation process. So I am giving a feed in one particular tray. This particular system has each and every tray from 0 to NT. So for the analysis, we took the same Leuben system. It has 21 tray system. In 21 tray system, we gave the feed tray at 10. So at the 10th tray, we gave the feed. Then we are giving a heat here, thermal energy we are giving. So if it is a liquid content, the liquid content will segregated in the bottom part, then it will boiled and vaporized. The vapor content will be condensed and the reflex drum will keep it, and again it will come to down. So this is the binary distillation column. Almost all industries we are using the distillation processes and all this with the binary distillation. Okay, there is no reaction taking place here. Simply whatever feedback or whatever feed material we are giving to the system, this particular system separate it into according to the products and byproducts. Then for this particular thing, how we can apply a backstepping technique? Clearly, in the beginning of the talk, I told that we need to segregate or divide the system into different subsystems. So that I am using a cascade control structure. We know that for the cascade control structure, we are having master loop and close master and slave. So the master and slave together, we have the cascade control structure. So the same backstepping technique we applied in this. So the dotted line represents master bar through slave. Then the red one is master slave. That means the dotted line represents a single PID controller. The red line represents a master bar slave cascade control structure using backstepping technique. You can see that here XD is the concentration. So you can see that here from 0.95 the set point starts. This particular case, we will get a stabilized concentration for red line in less than 5. But the dotted line with the PID controller produces a stabilized one around 10. Then the internal reflex drum ratio also like that. Same as XD, here you can see that the fluctuations are higher in the PID controller. But for the particular backstepping controller, we don't have that much oscillations and stabilized. Similarly, the same Lumen scientist made the objective known as reactive distillation column. The reactive distillation column is somewhat similar to our binary distillation, but here you can see that we need to give two feeds, feed A and feed B. The feed A and feed B, why we are giving this particular thing in between feed A and feed B, this particular portion is known as reactive section. That is stripping, reactive, rectifying. But in this case, we are having stripping section and rectifying section is there. But there is no reacting section. But here we are having stripping, reacting, and rectifying. So whatever data is stripping here, the reaction will be taking place inside this. This is known as control structure 7R proposed by Mr. Dr. Luben. The according to the Luben system, he implemented this control structure with a PID controller, and we tried to develop it with a backstepping technique. How this backstepping will function there? Maybe people didn't understand that what is this. I'm pretty sure. But clearly I can tell you to one point that you don't want to look into the meaning. You can look into this diagram and this diagram. This control structure with the PID for this control action, here you can see that initially the concentration is approximately 1. With increase in time, it is decreasing, and it is around 200 to 300 range. You can see that it is almost 0.78. This XB represents mole fraction per cubic centimeter of the particular product concentration. So initially at time 0, the output product concentration is almost 0.98, that is 98%. But when the time increases, the product concentration is decreasing to 200 to 300. In the time, it is coming to 78%. Previously, the concentration is 98, thus it is reduced to 78. With this, the Luben, if you look at the book also, you can see that the Luben proved that this control structure will not work for anywhere. There is a main problem in the control structure. By that reason, we tried with backstepping technique with simultaneous design and control. Then it is known in the new control strategy, we achieved that this 0.98 in that the concentration is not decreasing further. It is stabilized around 0.98. That means the concentration is almost stable. It is not fluctuating. Then from this we can tell that even if the PID fails this backstepping controller can able to perform this particular strategy. That means with the same structure, the backstepping can able to work with the same control structure and can produce better output. So these are the main researches happened in the control backstepping technique control strategy for industry processes. Along with that, this particular thing of backstepping, you can take that n number of purposes are available in our automobile industry, ship, everywhere we are using backstepping technique, even with the non-electrical components. Then, what is the particular thing for future research scope? Till a reactive distillation column be implemented. Then two, the ternary reactive distillation column is a complex task. If anyone wants to do research on backstepping technique means this is one problem for you. Implementation of backstepping technique is ternary reactive distillation column within it. Yet no one designed this particular process because the ternary system having three products. AB is the input and one output with some inert components. Many cases I also tried the backstepping technique there, but honestly telling, I too failed in that particular. My responses is sluggish and I didn't get a response there. So these are the one important point to you that you can take it as a challenge. You can be able to start doing your research on implementation of backstepping technique in ternary system within it. It's open problem statement. You can work on that. Similarly, one more new control strategy is recently arranged is known as simultaneous design and control. Till this, what we talked that we have a mathematical process, we are having certain control strategy. So with this, we are clubbing together and we are developing controlling an action. But nowadays, in the recent trends, changed to simultaneous design and control. That means we are designing a process. Before designing itself, we are writing the control actions also there. It is using MIDO. MIDO means mixed integer dynamic optimization. It is a pure optimization. You need to write the objective function, constraints, and all you can simulate. But this simultaneous design and control if using MIDO will not work good with MATLAB. Why? Because all these cases we are having generating certain unknown variables. These generation of unknown variables may lead to time consuming. Even I run this particular experiment in a processation, but I got result after, no, I got error after 12 hours. I continuously run. After 12 hours, it shows error with MATLAB. There is one software node GAMS, General Algebraic Modeling and Simulation. This software is exclusively we are using for optimization. If you are using this particular thing for optimization, you will get results in 45 minutes. You can randomly check n number of systems with this, but you should thorough about optimization. This technique is known as simultaneous design and control. So, along with the backstepping technique, if you implement simultaneous design and control, you are having a good research area on that. Whatever topic I already told here, we have certain issues, there is certain drawbacks. But now, the implementation of backstepping technique in ternary reactive distillation column inert, simultaneous design and control using MIDO approach, all these things are still yet to explore. So it's a vast area. You people can able to explore using backstepping technique and simultaneous design and control. So this is a briefing about what is backstepping technique and what the advantages of backstepping technique in comparison with the conventional PID or PD or PI controls. I'm just waiting for your queries. If anyone have more queries and if you want to make more clarity means, you people are warm welcome.
If you have any queries, you can just ask. Any of the doubt, you can ask, please, sir.
Sir? Hello, sir.
So one doubt. Yep.
Srilekha.
Yes, go on.
Hi.
Sir, I'm Srilekha. I have a small doubt. Recently, I have attended
Yeah.
a webinar
Yes,
based on.
Srilekha.
Sir, recently I have attended a webinar based on the topic sliding mode controller. Sliding mode
Yes.
controller. And sir, I would like to know what is the difference between this backstepping controller and sliding mode controller, and which one is better?
Both the controllers will work for same aspect. Okay, if you are going with a sliding mode controller, okay, that is, it is known as SMC. It is a nonlinear control method, right? That means it alters the dynamics of a nonlinear system by application of a continuous control signal that forces the system into slide along the cross section of the each normal system behavior. But in that sliding mode controller also, what we need to do is that we are taking the entire process model, entire closed loop control structure model. But in this case, we need to segregate or divide that particular system into different small pieces. In sliding mode also, the same Lyapunov stability criteria we are using with the Euclidean norm and neighborhood surface structure and the scalar control portions. Both the cases we can implement and cross-check both the sliding mode control and this, sliding mode control and backstepping control. But one advantage I found good in backstepping controller is this backstepping controller will get better result than the sliding mode control if we are having more nonlinearity. Why the more nonlinearity means, if we are implementing a sliding mode control, in some extent the integrator time will produce as a NAND. But with backstepping, I didn't find out any NAND. Hello? Srilekha? Is it clear, Srilekha?
Oh, okay, sir. Okay, sir. Thank you very much for this very informative presentation, sir. Thank you very much.
Thank you, Srilekha. Is there anyone having any other queries? You can unmute yourself and ask. Okay, I believe no one is having any doubt. So we are moving on to the next session, that is the vote of thanks. As we heard, Anisa took a very good session, informative session, starting from the basics of control systems, as well as what are the levels of control system and architecture of the system. Then he got to the backstepping control system, how it is implemented, how it is different from the normal conventional methods. All is defined very well in this session. That was a very informative session. So I believe everyone got the information, got the a thought that you like to convey, and it's been a very good pleasure for me to thank you in the name of our department for taking us such a very good session. Thank you so much, sir, for having you for our session. Now we have Professor Thomas George, our Vice Principal, who is our senior faculty in our department. He has been the convener of this webinar. So I would like to thank Thomas sir as well as Adira Shivanandan. She is an assistant professor in the applied department. She was a coordinator for this program, and I would like to thank all the faculties, all the head of the departments who have joined as well as who have taken part in this webinar. In the name of our department, we are thanking you all, and all the students who have joined this seminar. We are thanking you with our deepest heart, full of joy. Believe that you have got the information that you were looking for. And thank you so much for joining for our webinar. Have a nice day. Thank you.
Yeah, thank you, Thomas sir and Adira ma'am for giving this opportunity. Is Thomas sir here?
Thomas sir is here. Thomas sir. Sir Thomas sir is having some net issues, I believe. Is not
No
responding right
problem.
now.
I will contact him.
Yeah.
Yeah. Okay. No problem. Yeah. Thank you.
Yeah. Okay. Thank you, sir. Thank you, sir. Feedback have been provided in the chat. Everyone can fill up the feedback. Thank you so much.